Hi everyone. In this video I want to go over the mechanism of cyclic acetal formation. The example I've chosen is to make a cyclic acetal with this ketone with ethylene glycol. In this particular example, I am making the cyclic acetal to protect the carbonyl group, because maybe in a synthesis I want to do something on this side of the molecule with the bromine, possibly make it into an organometallic, but organometallics react with carbonyl groups. So in this case, I'm changing the carbonyl group into a cyclic acetal. Now, if you think about this protection strategy, to deprotect, all we need to do is to add water and acid to push the equilibrium back to the carbonyl group and the ethylene glycol. If I feel like I need to reproduce a mechanism, either for a presentation or a seminar, I like to memorize at least the first 1 or 2 steps of the mechanism. After that, I could probably use the intermediate products as clues or guidance to know what to do in the next step. In cyclic acetal formation, or just plain acetal formation, you want to protonate in the first step, then attack, have one of your hydroxyl groups attack. I also like to remember the number of steps. For acetal formation, there are 3 steps to the hemiacetal and another 4 steps to the acetal, meaning that there are a total of 7 steps. Whenever you draw a mechanism, you should always redraw your starting material, the starting material that will participate in the first step. And like I said, our first step is protonation. Let's protonate with HCl. Every step in this mechanism will be at equilibrium. You have to show the arrow starting from a source of electrons, which is typically a bond or a lone pair. And if you draw a lone pair on an atom, you should draw all the lone pairs on that atom, even if you're not using them. Let me draw the Cl minus out of the way. The second step I said was attack. We're going to bring ethylene glycol. It wasn't produced in the previous step, so we'll bring it over the arrow. And we have an attack. We are attacking this carbonyl carbon that has been activated by protonation. And, oops, one more mechanism arrow. And we get this intermediate product. Don't forget you have this methyl group on the dot, right there, and this oxygen is positive. Nothing happened to the hydrogen-oxygen bond, so you have to keep it. I said 3 steps to the hemiacetal. We're almost there. We just have to deprotonate this oxygen, and we could do that either with the chloride minus, or another water molecule, or another alcohol. Let me use, since I see it here, let me use this Cl minus. We have to draw the 4 lone pairs, because we're going to use one of them to deprotonate to get the hemiacetal. Did we truly get the hemiacetal? Let me shift this methyl group down, and I'll keep the alkoxy group up here. You notice that this alkoxy group has another hydroxyl group. That's going to help us cyclize very easily because of proximity. That is your hemiacetal. You don't have to label your intermediates when you draw a mechanism for an exam, but I like to remind myself, and I'm encouraged because I did get to the hemiacetal in 3 steps. In this 3rd step, we did create HCl, which is good because I'm going to use that to protonate the OH group. I mentioned that after memorizing the first 2 steps, the intermediate products can help guide you as to what to do in the preceding step. Well, here at the hemiacetal, if I look at the product, we have to get rid of this OH. So OH is not a good leaving group, but water is a good leaving group. We are going to protonate this OH group to make it water. And that's what I mean by using the intermediate products to help guide you to the next step. Now that water molecule is ready to leave, but it leaves in an interesting way in this acetal formation mechanism. Uh-oh. Forgot that arrow there. Let me put the chloride here. I don't know if we're going to need it or not in the next step. What I'm concerned about is now this intermediate, how to kick out water. We are not going to use this hydroxyl group in an SN2 type of reaction to kick out water. What actually does happen, and this is the step that you'll really want to focus on and study, is that you're going to use the lone pair of the oxygen of this hemiacetal to kick out water. We're going to make a double bond here, and we're going to name that type of group oxonium ion. So we remember that we have to form that in this mechanism. Do we have everything? We did kick out water. Again, not sure if we are going to use it. Probably not. Let me write it here. That is called the oxonium ion. And if you want to memorize how many steps it takes to get there, 1, 2, 3, 4, 5 steps to the oxonium. It's only 7 steps total, so we're almost there. Now that carbon is activated, it's more electropositive, and it will attract this oxygen here. I won't get into it, but why did I say this was more electropositive? It was because of resonance. You have resonance to put a plus charge on that carbon. Anyway, push the pi bond up to the oxygen and carefully draw what you think you have. We close the bracelet, and the bracelet has 1, 2, 3, 4, 5 atoms in it. So this dot, that's 1 atom, and we have 5 atoms, but 2 of them are going to be oxygen. Don't forget that. And I think we have, see, we have 2 CH2 groups. The thing is, this is still protonated, the oxygen that attacked. But we're almost there. We didn't create anything else. Let me use water to deprotonate this oxygen. I'll write it backwards like this. And I think that is our product. It got twisted around a little bit, but if you look at our final drawing here, it is the same molecule as our product, our target, and that is the acetal, in particular the cyclic acetal. And we created a molecule of H3O+. That can be used to protonate our next molecule as the reaction proceeds to completion.